So just you can start, right? We have a good number.
Yeah, I think so. All right, cool. Today we're discussing energy-based models and applications of energy-based models. So basically, the lecture was kind of broken up in broadly into what is an energy-based model and how everything is an energy-based model. And the second one was more about self-supervised learning. At a high level, it was about self-supervised learning. And then he talks about denoising autoencoders, k-means, and I think one other thing. So in any case, that's covered in this. So the idea behind, so the big difference between standard feed-forward or even convolutional networks, basically the entire idea is that given a feature set X, you are asked to predict a label Y, right? However, in certain cases, this is not very practical, and it's more practical that given a pair of feature sets x1 and x2, you try to find whether they are close to each other or not close to each other, right? So, and if they are similar to each other, some kind of measure of similarity. If they are similar to each other, the energy associated with that is low. And if they are dissimilar, the energy is high, right? So it's kind of like entropy, like the more you know about something, the more stable it is, right? Lower entropy versus a more unstable is higher entropy, right? So that's basically the EBM approach. And okay, so it says, what if the inference procedure is a complex calculation? Yeah, so there are various situations where feed-forward nets are not suitable. So these are the two here he's listed. What if the inference procedure is more complex? And what if there are multiple possible outputs for a single input, right? So so he talks about like an S-shaped manifold where if you clamp one of the variables, you could have multiple results on the points of the S, right? And okay. So this is basically, we already talked about. So then he says we define an energy function, which, this is the mathematical formulation. So it's an energy function f with, takes input x and gives an output y in a real number space where fxy describes the level of dependency between the xy pairs, right? So and he says energy is inference, not learning. And we will see that later when he talks about learning. But initially, his focus is on inference totally, right? So again, the gradient-based inference is that S-shaped example he goes on. And if you clamp one, and then you can do gradient-based methods to find out what each of the y values are for the given clamped x, right? And then the latent EBM with latent variables. Okay, so there is an extra spin here that not all EBMs depend solely on X and Y. Sometimes there is, if you bring in a latent variable Z, that can simplify your task, right? Or make intractable task tractable. So one example he gives is, if you have a spoken language, right? So you're trying to recognize speech in spoken language. If you do not know where the phonemes start and end, then it is harder for you to actually reconstruct the speech, right? Do the text-to-speech translation. He also covers very similar examples with handwriting analysis, and there is one other here where he talks about video, right? So example is translation. So this is more in terms of, one input string can have multiple output strings based on some latent variable. And that's what he says, there could be, for translation of German to English, there could be multiple translations to English that are all correct. And by varying some latent variable, you can vary the translation produced, right? And similarly with video production. So he gives a bunch of examples of this. So, but essentially it's, you introduce like a latent variable that you don't know, and the thing is that you don't have to know, right? The system kind of knows by itself, right? if you give it sufficient examples. So that was another example he gave where, and I don't actually remember. Oh, so he says like, if you look around the room, right, and a human perceives depth even without understanding the concept of depth formally, right? It just because he sees so many examples, and the understanding of depth becomes implicit to the um, their understanding of the problem, right? So, and he says like maybe this is something that machines can do as well. And then there is a lot of stuff here. So um, so energies can basically be thought of as unnormalized negative log probes. And so I have here, let me, I did my own notes as well as I was reading through. So there is something here. Any case, sorry. Yeah. And so essentially, you can. This looks like a softmax, but and this is the part where he says like energy is unnormalized log probability. So you have this. So you can basically exponentiate the log probability and get back the top part of the conditional probability here. And then this is typically the bottom is the everything else, right? So this is the baseline and this is the part. So you normalize the probability, right? And then if you have latent variables, then you can introduce that, and essentially you just change the function from the energy function from being a function of x and y. It's x, y, and z, and you do the same thing down here. And then you can marginalize over, I think this should be z. If you marginalize over z, then you can essentially take this thing. Oh, okay. You can, oh, so this one he does like, it's basically just, math transformations. He multiplies and divides by beta, and then he does a log of this, right? And so essentially, so log and exp of this, right? So log, yeah, sorry. So exp and log of this, and inside he multiplies and divides by beta, right? So the idea is to get back this variable, right, which we have already defined earlier as f infinity. Where is this? It was somewhere in the lecture. He declared it earlier as f infinity. So let me go back to my notes. I think I can explain this better here. Eliminating z. Okay.
Yep. Here we can also intuitively think of it as the energies. Uh, uh, in the tutorial that I shared just before the uh, chat on page number 6, there is a total explanation through an example.
Okay, let's go look at that. 6. Yeah, this is like I saw it this morning, and I just skimmed it. So it's it looks like really awesome. So
Yeah.
very very
This.
detailed.
Yep.
This one, page number
Yep.
6,
Yep. Section 1.3, in
1.3.
which,
Okay.
yeah, he decides the decision making versus the probabilistic modeling, and
Okay.
what's
Yeah.
the guarantees with respect to the energies or the all the possible outputs, and how it is transferred into a normalized probability distribution.
Yeah, this bit, right?
Yeah,
Equation 2.
yeah,
Okay.
equation two.
Right. Yeah, this part is kind of similar. What I'm trying to look for, so in the lectures, there was, where he takes f infinity, right? Then he kind of says, okay, this is f infinity, and this is, if I change it to beta, then it becomes this, so that's what I was looking for. And I cannot find, oh, here, sorry. So, so eliminating z, you get the f infinity of xy is min of, the energy function of x, y, and z with for the minimum z, that is the f infinity. And f beta is, as beta goes to infinity, reduces to above. So this is the part I was trying to explain here. So f of beta xy is 1 over beta. So how he gets this is what I was trying to explain, but it's explained in the lecture, and I don't remember how it is. But essentially, he's trying to get to this point, right? And so he can, replace, get to this formula, right? So you take this and replace it with that f beta, and that's what I was trying to get to here. And then, yes, go ahead, Mike.
Yep. This is a free energy formulation. So, yep, we can also understand this in the terms of, I think so, they have given it in the uh, tutorial too, with respect to the formulation of how this is calculated. The the transformation of 1 by beta log from 1 to z, the exponent over minus beta, and the energy over x, y, and z. It's kind of a elimination of the probabilistic latent, such that it's been kind of like uh, summed up to one. So it's like it's a total marginalization in a way that these uh, functions have to be, how do I say it, pretty at loss for the exact word of how he puts it, but it's in the document. Try to find the page. Yeah, please continue. I will share.
Okay. So, so basically, this bit is what he calls free energy, and this can be very hard, and in most cases intractable, as he says. So, and minimize corresponds, then okay. Or if you have a latent variable you want to marginalize over, and minimizing corresponds, just an application. So in any case, physicists apparently call this free energy, so that's why they call it F instead of E here. And so I don't actually have an intuitive understanding of what the free energy is. So if Mayank or others have it, then please interrupt. But this is his basic formulation, and so he basically talks about free energy being, or sorry, the energy function being like a manifold, right? So rather than being like, what we think of as, given input X, we try to get a label X. This is basically like, you can think of the XY space in 2 dimensions. And then these are like the energy function basically represents different manifolds in this space, right? And so this is again if you think, so then he gives you an example of, trying to predict masked words in a sentence versus trying to predict the next action in video. And he tells you, obviously because video is continuous, and it succeeds in the case of masked language models, where it produces believable answers, like may not be exactly the same as the input, but it those are okay answers, right? The masked words that it guesses are appropriate. However, in case of images, because the images are continuous and the space of possible images are infinite, it is a harder problem. And usually, if you just use maximum likelihood, all you'll get is a blur, because there are multiple possible actions that are possible, images, scenes that are possible, and the average of all is just a blur, right? So, so he says, like, the typical approach of trying to predict the softmax of all possible possibilities is not feasible here. What is more feasible is that you clamp one of the features and then you look for possible values of the other ones, right? So what is the rest of the feature set, or the y value in this case? So I think of it more as x1 and x2, right? So if you think of those, so given a and a record, find similar records, right? So you can find, like, if you clamp it this one, so you're looking for records which are similar to the one given by x. So you can find 3 of them in this case, right? So that's pretty much it here. And then he goes into, like, why Bayesian, if you think of it in Bayesian terms. Oh, I see. Okay, there's one more thing here. So one other point he makes is that in the mathematically, this manifold is basically an infinitely thin line, right? So really, these points are meaningless, because if you think of gradients, this is going to be like a Dirac curve, right? So it's like 0, 0, 0, 0, 1, and then 0, 0, like a discontinuity, right? However, you want, as a Bayesian, you could say that my priors say, I would say that my prior says that this curve is smooth, right? And so therefore not discontinuous. So then he says, if you're going to go that far, it is the same as an energy model. So here he says that you could think of this as a prior, but everything you do in Bayesian terms, take the logarithm thereof, forget about normalization, and you get the energy-based model. So again, this goes back to his thing that everything is an energy-based model, right? So, with certain caveats. So in any case, this is what the first part was. The second part is more practice-driven. So he talks about self-supervised learning, and so it used to be called unsupervised learning, and the objective of self-supervised learning here is to learn a good representation of input given massive amounts of input here. So for instance, BERT is an example of self-supervision. Obviously, we all know that. And the denoising autoencoder, which is an older architecture, is also an example of self-supervised learning. In fact, he goes into a bunch of different things that you can think of as self-supervised learning as well. So you can, here are some examples: predict the future from the past, predict the masked from the visible, occluded parts from available parts. So again, he goes and talks about NLP and computer vision as two big branches where this has been applied. And he finds that NLP has been more successful in using this approach than computer vision. And one big reason for that is that the space of possibilities, for the masked pieces in computer vision, the space is continuous and infinite, and therefore it is not feasible to do it with this. But and if you look at
so I have a question about that. When I was listening to him say that, when he said that the images are continuous, but they can be made. I mean, they don't actually. They're not continuous because the pixel values go between 0 and 255, and the only reason why they're continuous is because we renormalize them to be from 0 to 1, so they become floats.
Right.
If we maintain the pixels in their original form, where they're integers, the pixel values, then it's not a continuous model. So I'm not sure what he means. Maybe he just means it's just extremely high dimensional. I mean, the number of possible configurations of an image is really high dimensional, is astronomical. Especially if the image is bigger than any image. Even a 32 by 32 image has a very large number of possible configurations.
Right.
So maybe that's what he means. It's not really continuous. It's just extremely high dimensional.
I think you are right. Also, he does mention that you can bin. So, going back to this, so really, I mean, even if it was continuous, you could go back to the 128, 0 to 128, right, and bin them, right?
Yeah.
But he mentions there, and I think that's to your point of being high dimensional and hard, right? So he says it's almost intractable to handle that kind of thing, right? So that's
yeah,
right. Also, the other thing with NLP, I think, is words have meaning, right? I guess pixels have meaning too, but I think words have more compositionality than individual pixels, right? Groups of pixels I can see as being word-like, right? But just an individual pixel, like a piece, a little brown dot, it could occur anywhere, right? So that's another thing I think goes back, and maybe it, you can think of it nicely and put it succinctly, and it's high dimensional and hard, so hand wavy terms, right? So yeah,
totally agree. There's a cool figure on page 22 on the tutorial.
Okay.
Page number 22, and there they have bent the face, the picture of a face. So here from here we can get a intuition of the latent space and how that are built into from a continuous to a discrete domain. So,
I see. Okay. So
it's the same kind of meaning that is applied here with respect to the kind of space that he showed for the French words, which was particularly difficult to.
Right, the long sequence that he says, right? Yeah.
It's kind of like say, and the threshold with the no phase, the energy waves detector can locate and detect the phase by using the location of those latent variables. So basically, what we can do is have a kind of a knob too for changing that latent variables depending upon the regularization parameter that we use, and that will output that.
And you can basically move the face up and down or sideways in this in the second picture, right, by changing the value of z.
Yeah, from the principal components, yep. But here it's with respect to more the continuous and a discrete copies that are routed to the output energy. So it's a bit different. It's locating the best scoring location in the image. So it's kind of like where the face was found and how the resulting value of z will indicate the location of that particular pixel. So yeah, it's a bit different, but yeah.
Okay, cool. Yeah, I actually wanted also to point out here. So this is Arthur's blog post that he shared earlier, and he kind of so this is also Jan LeCun, and he goes down here and suggests a using self-service. So they have this not this, okay, this. So he talks about there, the SWAV method. This is something that these guys are working on at Facebook.
Sorry, could you share that, please?
Sure.
I didn't see it in the Slack or anything.
Okay, yeah, okay. Hang on, let me figure this out. Sure. Chat, right? Chat. Chat. Yeah, sorry. So here, this is on the Slack channel like a week or so ago. Right?
Oh, okay.
Yeah. And I really wanted to call out these two, Mayank's paper. Unfortunately, I received it this morning. Well, I saw it this morning. Maybe you sent it earlier. And it's 60 pages long. So, all I did was just, skip through it. But I think this is like an awesome resource. I think we should have, had I got it earlier, I probably would have made better use of it. In any case, but it's always we can always go back and read it later.
Yep. Totally agree.
So then he talks about predictions for the next frame, and there are two kinds in general that he of the energy-based models. One is conditional, where you talk about the compatibility between X and Y, and the other one is unconditional, where you measure the compatibility between the components of Y. So here, I think then he goes and talks about training. Okay. So so in training, there is contrastive methods and there is architectural methods. And he lists out 7 different ways of doing it. And here, so in high level terms, contrastive methods involve pushing down on fxy and pushing up on the other points. So fxy is the manifold, basically, right? So you push down on that and everything else automatically goes up, right, on the energy. And with the architectural methods, you build your fxy, so the volume of low energy regions is limited or minimized through regularization. And there is, I don't have a very good, pictorial, intuitive feel for that. But in any case, so he talks about 3 different kinds of contrastive methods. In the first case, you push down the energy of data points, up everywhere else. This is like maximum likelihood. And then second one is push down an energy of data points and up on chosen locations. And so not only do you push down the on the manifold, you also take certain locations and push them up. And he shows you how in the contrastive divergence example, which we'll cover later. And there are, so he lists out different things like contrastive divergence, metric learning, ratio matching. It's there in the slides. And C3 is you train a function that maps points off the data manifold to points on the manifold. So this is like denoising autoencoder. Again, the example, there is an example which is slightly more intuitive than just definition here. Architectural, he's got 4. And build the machine, so volume of low energy stuff is bounded. PCA k-means, he talks about k-means, so I'll cover that as well. Use regularization term that measures volume of space with low energy. So these are like high level things. I mean, it's there, but I think if you look at examples, that might make it clear. He doesn't give you examples. I think next week is Alfredo does a few examples. Yeah, so A3 is make the GXY as constant as possible, is contracting a autoencoder, saturating autoencoder. And A4 is score matching, minimize gradient. So these are like, I just got it off his slides, but then he says, okay, so again, this goes back to the conditional models and unconditional models. You're trying to minimize the energy model over the keep over all values of z, and then you find the minimum energy, right? So that gives you your free energy, maybe F, yeah. And then you can get F beta, which is I think this goes from the Gibbs-Boltzmann equation or something, right? It came from. Maybe it comes from that, right? Oh, the negative log probability. Sorry. Yeah, okay. Energy is negative log probabilities. Therefore, you can represent it like this, because if you multiply it, the negative. So e to the power minus energy is the inverse of the log, right? And then you multiply and divide by beta. I think maybe that's what the formulation is here. And unconditional is basically Fy measures the compatibility between the components of Y. And I think unconditional k-means is an example of unconditional. So the idea is that if you think about k-means, you basically pick k centroids or k points to be the centroids, and then you try to cluster the other points around those k points, right? So what they are doing here is they're selecting a random weight vector, and they're selecting a value of k, corresponding to the k points that we pre-select in k-means, and the number of columns of this random vector w is k, right? And so then you take one of the points here and you try to find the closest point, the column in w, which is the closest to the point selected, and that is your your candidate centroid, right? And then, but you know the labels, right, while you're training. So you're trying to minimize the distance between your candidate centroid and the actual centroid. So that's basically the idea behind the k-means formulation here. And he shows you here that if you now plot energy, you'll find that just around the place where the clusters are, so this is a cluster, and just around this is regions of very high energy, and whereas within the actual cluster, it's it's quadratic wells. Sorry, so this the black blob surrounding the line corresponds to quadratic wells. So actually low energy. Sorry. So these are like very low energy situations. So essentially, it's like a manifold. And if you think of the gradient, it's like very it's like a valley, like a very narrow valley of on the gradient. So that's the k-means example. Then contrastive methods. So here it says, according to Dr. Jan LeCun, everyone will be using architectural methods at some point. But contrastive methods actually work for images. And so he says, consider the figure below. I don't know about you, but when I was watching the video, it was like very unclear to me, what this thing was. I had to look at the notes to figure this out. Because I wasn't able to see, how he was handling the, where the manifold was and whatnot. So in any case, so here is a manifold, and here is the energy map at the, at a certain point in time, right? So what he does is here is he takes a single one, and he covers the denoising autoencoder, and he talks about I think contrastive divergence later on. So in the denoising autoencoder, what you do is you take each of these points and you perturb them, right? And then anywhere where you perturb them, you say, okay, this is a region of high energy. So essentially, as you move this around here, you're creating local high energy areas here, and over time, you kind of create this massive, valley sort of formation, right? Which so that's how the denoising autoencoder works, intuitively. And if you have a corrupted data point, so as you corrupt it, you push the energy up, right? So, and over time, it'll, again, we already talked about this. So, and this is just a flow diagram for doing this. I mean, you take Y, you corrupt it, you encode it, decode it, and then, you get back a portion of Y bar here. And then you say, Y minus Y bar squared, and you try to minimize that, right? So that's your contrastive thing. And he says if the denoising autoencoder is properly trained, the energy would grow quadratically because your loss function is quadratic as we move away from the data manifold. And okay, and he talks about BERT very in kind of passing. So he says BERT is trained similarly, except that the space is discrete. So as we are dealing with text. And the corruption technique consists of masking some of the words, and the reconstruction step consists of trying to predict these words. We know that, right? I mean, BERT is kind of, yeah. And in case of contrastive divergence, it's again the same kind of manifold with, the contour at some point in time, the gradient, the contour map of the gradient. And what he does here is that he, it's like rolling a ball from each of these points, right? So you start a ball off and maybe it rolls here. And wherever it rolls, you basically increase, you raise the energy of that, right? So all the points that it rolls down from, now starts going up, right? So again, you have this valley kind of shape, and that's pretty much it. Yeah. So, and that's how you basically get that you get the manifold of low energy, and that's basically all there was. Yeah, I don't think I have anything else here. Yeah, and yeah, so that's what I got from the lecture. I mean, obviously, if people have been working with EVMs or they have more interest, like the previous interest in EVMs, I think Mayank does. I mean, please chime in, and we can keep.
Yep. I would just like to add in the thing with respect to the how do we push down the energy of a data point and the push up everywhere else. Let me try to
Yeah, I'll stop sharing. You can share if you want.
share my screen. Yep. So here the simple examples that we got with respect to the k-means and this guy. What was the spiral plot, and that puts us point on the data manifold, which we had with respect to the regions of the anchor points that we k points that we had, and the high energy that kind of grew quadratically. So this is the formulation with the PCAs and the k means which they are used here. So I think so. This was given in the slides. Uh, this was a kind of a example with respect to the maximum likelihood learning and how we push it. The uh, partition for functions here. So how can we make this the upper numerator big and the negative log likelihood small, so that loss function is the energy with respect to the high uh, uh, labels have proper the high probability of the labels have the high energy versus the other thing. So that's vice versa. Uh, such that we minimize on the training samples. This guy here. So this is an intuitive understanding of how from this to this. This is the correct one, and the probability to the expectations how it pushes up. Yeah, this is the mathematical formulation of the optimization a function that follows inside at each epoch. Uh, we can also view this in a separate way here, uh, how it intuitively works, how it is actually pushed. Yeah. So this example, if everyone can see, this is the 4 intervals of the energy training and how the manifold is taking its shape. At the start of the training, this is at A, after 10 epochs at B, after 25 epochs at C, and after 39 epochs at D. So energy shape, how does it take the dark spheres and the low energy all around the point? So this is the uh, uh, 3D representation of this. Here, I think so. They have taken 10-dimensional output unit. So this is with respect to the example here. But yeah, this is the reshaping of all the epochs and the energy points. But and then he also discusses the Monte Carlo MCM Markov chain and the Hamiltonian Monte Carlo methods, and
Yes,
how do they
remember that. Yeah. Okay.
and how do they optimize it? But uh, with respect to the example, I think so. he had this guy here. So this was the intuitive representation of how the actual loss function, the perturbations and all affected the and then the projection and what happened to the loss landscape here. So this is the red guys was the denoising autoencoders. The yellow guys was the contrastive. There were two other things. Yeah, Monte Carlo and the MCMCs and the Hamiltonian too.
Right, yeah.
This was kind of cool. In the figures, I think so. In some other presentations, he might discuss this too in the future. There were a couple of other things with respect to the figures that he drew in the training of the this guy. The how do we have the decision boundaries that take shape? Uh, uh, and what is the objective here, the loss that we have, and, uh, and how it differs from the I think so. He also compared it with the GANs too, or it was in the paper. I don't remember exactly. Yeah, but these two perspectives were kind of cool.
I think GANs are basically an example of energy models now. I mean, because you have one component trying to generate, latent points, right? And the other component basically saying that, okay, this is good, this is bad, right? So in some respects, I think,
yeah, in some respects, it is. We can of course think of that as an example of a because that has a min-max objective, and that firstly it is used to identify those decision boundaries. Then it clusters around them. So yeah, that can be thought of like that. Other than that, I think so. Yeah, this was it.
Yeah, other thing, the Arto's blog post, the Jan LeCun blog post that Arto shared, that also has an example of Siamese networks. So a lot of us have probably used Siamese networks. So we used an energy model, without knowing what an energy model was, I guess.
Yep, totally agree.
So that's, I think, okay, go ahead.
Yep.
Sorry. Yeah.
Other than that, if you guys need to know some of the research papers that have recently been published with respect to the energy-based system, there were a couple that I found intriguing. One was, let me try to share the links in the chat. One was this. Your classifier is secretly an energy-based model, and you should treat it like one. Uh, everything can be viewed from a perspective of an energy-based setup. This was published in iClear in 2020, last year. So here they took the classifier. They had a very good explanation and visualization from architectural point of view. The accuracies and the other stuff that we just had overview of. They had gotten deep into the nitty-gritties of the optimization, the calibration, and how can we regularize it, all that stuff. And plus the robustness of the classifier, how the decision boundaries can be correctly updated, how the out of distribution stuff can be detected, Yeah. And the other was this paper, which I found out about yesterday. This was Sentry. This was a cool paper with respect to the entropy optimization. Here, what they have done is here what they have done is, and let me try to share my screen again. So this was with respect to the joint energy model, the earlier paper, that your class is secretly an energy-based model and you should treat it like one. Uh, it rivaled the GAN-based approach. And how can this energy-based function serve as a uh, 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 example to take samples from MCs and how to view it as a density model. They interpreted this classifier as the gem.
Okay.
Yeah. So this was it. They applied the identity and the logs, the softmax and the neural networks layer to have a representation of the feature space. The other one was here. This was a selective entropy optimization. So here, what they do is they try to have they try to fix those distribution shifts um, that has errors under the uh, cross-domain label shift. So if you see this figure, the figure 1 here, this is kind of a poor initialization, and if we try to minimize the entropy, how the error is accumulated, you may see this kind of a triangle and a circle. These are two classes, and it's incorrectly accumulated. Those clusters are incorrectly formed. And if we use this selective entropy optimization, so how is that actually gone to form a proper robust domain alignment function, which can correctly classify those labels? So this is the kind of objective or the confidence set that they produce in trying to have, and it had this significant improvement, and it reached the state of the art in 27 out of 31 domain shifts from this UDA benchmarks with respect to the label distribution shift in those settings. So yeah, that is critical in a way that we see the conversations that are currently happening, in which the folks are currently focusing on trying to solve the uh, problems in the, if I talk about naively in the sense of those biases and distribution shifts that's happening all across it, and maybe this kind of a approach may help. Oh, obviously, there will be challenges with respect to the scalability of it, but yeah, since everything is nowadays extension of a uh, uh, semi-supervised approach, so we need those predictive entropy increases or that robustness in our classifiers to have that balance autocorrect. Yeah, right. That was my 2 cents here. Thanks.
Thanks, Mark. There's like really good stuff, and a lot of reading to be done now. For
Plus, they applied this the Sentry stuff on the real world with respect to trying to have the data sets in a form of a clip art domain. So that was cool too. The stuff that we had in Microsoft Office as a child, as when I was a child, I played around with it quite extensively.
Hey man, a question, like not question, maybe request. Maybe you would have some project you would like to like make a demo for us of application of some of the work we are talking about here,
Yeah, I can.
Yeah, maybe for some like either next week or in 3 weeks there would be this like our session for practical part, which I think I was scheduled to lead, and maybe we could like split it into, and if you have some like relevant work you would like to share, it would be cool.
Yep. Yep. I should be. Okay. Yep. Yep. I will. I had a couple of things that I was working on. Yep. I will check it out, and we can connect on Slack, and we can share what we have there.
Yeah, cool. Maybe we could, I don't know, work on some small project. We would like highlight some nuances of this, and that would be interesting, I guess.
Yep. Cool.
Yeah, cool.
Yeah, that sounds like a great idea, Otto. Thanks, Sujit. Thanks, Mayank, for sharing all the resources.
Right.
Yeah, and yeah, I don't know how Mayank finds the time to read all these papers, to be honest. Okay, do we have any other questions? If not, we can end this call. Also, the next lecture is on practicum of autoencoders, I think. Sujit, if you want to continue, feel free to do so. You can take that up, or if anyone else is interested, I'll make a post on Slack. So
Yeah,
that
I can do that. It's not a problem. Yeah.
Okay.
It's,
Yep. That's
might
great.
as well, keep going and do a little bit more. Yeah.
Yep. Sounds
Cool.
good.
Yeah. All right.
Okay. Thanks, everyone.
Sure.
Bye bye.
Thanks. Take care, guys.
All right.